So thank you for the introduction. My name is Dmitry Chistikov, and I'm going to talk about subcubic certificates for CFL reachability. This is joint work with Rupak Majumdar and Philip Shepa, and I think Rupak is here in the audience. So I'm saying hello from the United Kingdom. So and maybe firstly a brief summary, like a one-line summary of this paper, is that we're trying to understand. This is an attempt to understand the subcubic, the cubic bottleneck for CFL reachability. And while we don't have a truly subcubic algorithm, we have maybe something like it. So so this as this was a CFL reachability session, effectively, I suppose I shouldn't say too much about the problem in general. So CFL reachability appears under, and related problems appear under various names in various areas in computer science, in model checking, in formal languages, in graph databases, and of course in program analysis. So I'll say maybe just two words that for CFL reachability in general, and I'm thinking about, let's say, reachability for the language with two kinds of parentheses on a graph on n vertices, the best known worst case upper bounds are cubic that are already celebrating 40 years in 2022. And this was beaten by a logarithmic factor in Popple 2008 by Swaraj Chowdhury. What is the best lower bound? Well, there are several lower bounds of the form n to the omega, where omega is the matrix multiplication exponent. So put briefly, it's very unlikely that you'll manage to solve CFL reachability faster than you can multiply two matrices. And there are multiple reductions that you can find in the literature, and some of them relate this problem to problems such as k-clique and problems such as Boolean matrix multiplication by, in particular, Andreas Pavlogiannis, who gave the talk just now. But in a sense, it is unknown whether an algorithm with running time, let's say n power 2.9, is possible. None of the existing reductions actually rule it out, but there is no algorithm with this running time. So let me say that this picture was somehow made possible by a profound result by Leslie Valiant, who showed in the 1970s that a related problem, namely of CFL language recognition, can be reduced to matrix multiplication. Effectively, if I give you an input word, you can decide whether it belongs to a fixed context-free language in matrix multiplication time. CFL reachability is a more complicated problem, and we don't know if an algorithm like Valiant's algorithm could exist for CFL reachability. And that's an open problem, and this was mentioned for example, in Swaraj Chowdhury's paper in Popple that I mentioned. So he points out specifically that it is a hard open question whether all pairs CFL reachability can be reduced to Boolean matrix multiplication. Let me say that, let me actually formulate a slightly more general problem. Is there a truly subcubic algorithm for CFL reachability that is one that has running time m power 3 minus epsilon for some fixed epsilon? And you can think of this as whether there exists an algorithm with running time n power 2.9. And this is an open problem. Let's turn this problem around slightly. Let me ask instead whether we can find a stronger lower bound than matrix multiplication time, than n to the omega. So at the moment, you can think of omega as something like 2.4. That's a safe upper bound. We know lower bounds of this level. Can we find a stronger lower bound for this problem? Well, firstly, what are lower bounds for this problem, and where do they come from? There is a whole area that's maybe about 20 years old now, of so-called fine-grained complexity and fine-grained reductions. And this area connects different problems. Many of them can actually be solved in polynomial time. And this is not unlike MP completeness, MP versus MP, but within polynomial time. Although not all the problems in this picture are in polynomial time. So this is a figure from a paper from 7 years ago by Virginia Vasilevska-Williams that's showing a net of reductions between different problems. And of course, since that survey was written, the many more reductions have appeared. The result of our paper can be summarized if in one sentence in the following way. An appropriate reduction from SAT, from Boolean satisfiability, to CFL reachability would have significant consequences in circuit complexity. So let me explain what I mean by an appropriate reduction. So this would mean a reduction that gives us a stronger lower bound than matrix multiplication time. And I mean an appropriate reduction from SAT to CFL reachability that we would like to show stronger lower bound. So if such a reduction is possible, this would have significant consequences. Now, what is the main idea? And again, this is just firstly a summary of our results. The idea is something called certificates. And this means if I have an instance of the problem of CFL reachability, then I can try to convince someone else that a given instance is a yes instance or no instance. In principle, you can try to just run the algorithm for CFL reachability and see that the algorithm, let's say, returns a no, and this is convincing, of course. But maybe there is a way to convince someone faster. And our main theorem, again, I'm hiding the definitions here. CFL reachability has subcubic certificates, and here by subcubic I mean truly subcubic. So they have actually a quadratic size and can be verified in matrix multiplication time. So how does this relate to the open problem? Well, it turns out that because of the existence of the certificates, we can rule out reductions from SAT. And you can read the text here that says, oh, if such a reduction exists, then some hypothesis is violated, and this implies a better proof system for tautology. The upshot is that if such a reduction exists, then you can convince someone that a given SAT instance is unsatisfiable. And in the worst case, you'll do better than just enumerate all assignments. And no one knows how to do this at the moment, and this would be a breakthrough. So this slide with the summary will serve as the outline for the remainder of the talk. So I will first talk about certificates and subcubic certificates. And then I will show connections to fine-grained complexity and why this will break reductions from SAT. So onward to the first part about subcubic certificates. Maybe just a brief brief slide to fix the notation. So when I say CFL reachability, I will think about Duke 2 reachability. So this is a problem where the input is a directed graph, and the labels and there are labels on edges. So sorry, there is a typo. So labels should be on edges, not on vertices. So and there are two kinds of parentheses: round parentheses and square brackets. And I have two vertices S and T. And the question is whether there is a walk in this graph from S to T that's labeled by a Duke 2 word. And here are some examples in blue of words that are well matched and words that are not well matched in red. So I will be talking about yes-no version of the problem. But in fact, our results will apply as well to the all pairs version of the problem, where I'm asking this for all possible S and all possible T in the graph. Okay, this was just to fix the notation. So let me talk about certificates. So there will be certificates for reachability, so for yes instances, and we also give certificates for non-reachability, for no instances. I think the latter are somehow more interesting, and I will focus on them in this talk. So Let me start with an abstract example. It's a special case. Consider first the usual reachability question in a directed graph. There are no labels, no edge labels. Suppose I give you S and T. How can I convince you that a vertex T is not reachable from vertex S? So certificates I can use as a certificate a cut in the graph. I can find the set of all vertices that are reachable from S. And from this set, there is no edge leading outside, right? Because this is a set of all reachable vertices. Now, if S cannot reach T in the graph, then of course T must be on the outside. Therefore, by presenting this cut, I will convince you that S cannot reach T. So you can easily verify that indeed, there is no way to go from S to T. So we generalize this idea to CFL reachability. So, and here is how we do this. So D2 reach here denotes our version of CFL reachability with two types of parentheses. And what we do is we construct the well-matched reachability relation. So given a graph and given the edge labels, let's consider the set of all pairs S and T such that it is possible to reach T from S by a well-matched path. So this formula here in the middle, it basically says that the instance with S and T is a positive instance. Right? So this is kind of the reachability, all reachability pairs in the sense of Duke 2 reachability. So the certificate will be this relation that I write as a matrix. And here is such a matrix. So this would correspond to a graph on 5 nodes. And this would say that vertices 1 and 2 can reach all other vertices and themselves, but vertices 3, 4, and 5 cannot reach vertices 1 and 2. Right? So this is the kind of relation that I could use. Now, more formally, a certificate is any 0, 1 matrix of size n by n, where n is the number of vertices, that satisfies these 5 relations. And these relations you can check quickly, but let me try to read these 5 conditions slowly and interpret what they actually mean. So the first inequality, I is at most m, where I is the identity matrix, basically asserts that kind of a purported certificate, so someone gives me m and says, well, that's the reachability relation, or at least the reachability relation. So the first condition, I is at least m, says that every vertex is reachable from itself, because the identity matrix has ones on the diagonal. Now, the condition below it, that m squared is at most m, basically encodes the following intuition. If there is a well-matched path from U to V and a well-matched path from V to W, then there must be a well-matched path from U to W via V. So this is how matrix multiplication really works, and I remark that multiplication and addition here are Boolean, right? So whenever I say matrix multiplication, this is over the Boolean semi-ring. So now the two conditions on the right say, oh, if there is a path from U to V that is well matched, and you can prepend this path by an open bracket and append a closing bracket at the end, this is also a well matched path. And then the same for square brackets. So these are these two conditions. And then the final condition basically says, oh, and in this relation that you give me, there is no path from S to T. So the intuition behind the certificates is actually, this is kind of an over approximation of this well-matched reachability. If these 5 conditions hold, then we can be certain that M is an over approximation of the actual reachability. Which means that, well, if there is a 0, then this must be a 0, then there is no reachability. So this basically encodes a form of invariant, although I will not say precisely, the word invariant, because this is something slightly different. So as a consequence, we can show that these certificates, these matrices, well, of course, they have quadratic bit size, And it's possible to prove that a given instance of CFL reachability is a no instance if and only if there is such a certificate. And this follows the intuition that I just shared. And of course, you can check that certificates are valid in matrix multiplication time, because what you really need to do is you check these 5 conditions. So the consequence of, and maybe I'll give one remark. You can think that, well, matrix multiplication, it is subcubic in theory, but maybe in practice it's more complicated. In fact, you can, instead of running actual matrix multiplication, you can run a similar algorithm that verifies matrix multiplications. And this will be a randomized algorithm that works in quadratic time. And it has nice properties that I will skip here. So, so this is the intuition behind certificates for reachability. So these are short certificates that can help me convince someone else that a given instance is a no instance. I don't know, so I described how to find it, but of course, given an instance, it's kind of tricky. It may be tricky to come up with such a certificate. So, and there are also certificates for the positive instances that I'm not showing here. And the conclusion is that both positive instances and negative instances have subcubic certificates, in fact, quadratic, that can be verified in subcubic time, in fact, matrix multiplication time. And there is a way that this theorem extends to all pairs CFL reachability that I'm not showing in this talk. Please ask me if you're interested. And one way in which you can kind of formulate this result in a complexity theoretic way is to refer to non-deterministic algorithms, because you can guess a certificate, and this corresponds to non-deterministic time or co-non-deterministic time. So I will not spend more time on this. So so that's it for this part of the talk. And let me now move on to consequences of subcubic certificates. I think I should have maybe 5 to 7 minutes, as I think we started slightly late. So I promised I will talk about fine-grained complexity. So fine-grained complexity is basically the optimization of the exponent in running time bounds, kind of put, at a distance, right? So so what does fine-grained complexity do? It basically finds links between different problems, and links are called fine-grained reductions. For example, you can show that a problem A reduces to problem B in linear time. Or you can show that problem A reduces to several subproblems of the form B of different sizes. And this is actually the case for the Valiance result, where he shows that CFL recognition reduces to several instances of matrix multiplication of different sizes. So now in this theory, instead of the classic hypothesis that P is different from NP, new hypotheses appear. Let me say a few words about them. So, and these will be hypotheses on the computational complexity of unsat. And unsat being a problem where I give you a Boolean formula in conjunctive normal form, and I ask you whether it is true that it has no satisfying assignments. And let's n be the number of variables. So, of course, you will have heard about P versus NP, and this basically says no matter what constant C you pick, there is no algorithm for unsat that runs in time n power c. A stronger hypothesis is called strong exponential time hypothesis. And simplifying slightly, it says that there is no algorithm that runs in time 2 power 1 minus epsilon times n. And this works for every fixed epsilon. So this is a stronger statement than P versus NP. If this holds, then certainly P is different from NP. So strong exponential time hypothesis appears as the source of many reduction in this fine-grained world. So in this picture that I showed you previously from Virginia Vasilevsky-Williams's paper, so you'll see K-sat in the middle, and that's basically SETH, right? So this is this hypothesis that I just mentioned. So now, about 6 years ago, a new hypothesis was introduced, which is called non-deterministic strong exponential time hypothesis. And it says that for this unsat problem, there is no non-deterministic algorithm that runs in the same time. So even for non-deterministic algorithms, this is impossible. And what does this mean, non-deterministic algorithm? Basically, this says that there is no short certificate for unsatisfiable instances, right? There are no short proofs that a given instance has no satisfying assignments. So this was introduced in 2016 by the San Diego group on computational complexity, whereas SCTH is already more than 20 years old. So why am I talking about this hypothesis? Because our main result for this part of the paper is if the non-deterministic SCTH holds, then there is no reduction from SAT to CFL reachability that gives us stronger hardness than matrix multiplication. So there is some formalism here. This basically says exactly what I said previously, right? So this rules out reductions from SAT. And let me show in the, right. So let me just say that what is this new hypothesis? Can this fail? Well, it can fail, but if it fails, we automatically get circuit lower bounds that no one knows how to obtain. Basically, there are interesting consequences, very interesting consequences of NSCTH that everyone would love to have, but no one knows if that's true or false. All right, in the remaining time, let me give you an intuition for why short certificates imply this strong property, right? That will rule out reductions from SAT. So in general, what is a fine-grained reduction? I said problem A reduces to problem B. What does that mean? Roughly speaking, this means that you can write a program, an algorithm, where the only input is X, some instance of this problem A. So something is going on, and then this problem uses as a library call, as a subroutine, a procedure to solve problem B. And it calls problem B on certain instances. Here it's instance P and instance Q, more stuff is happening, and then some result is returned. So, and then if running times are kind of composed in the right way, then this indeed shows that problem A reduces to problem B. So as an example, SAT reduces to some problem called orthogonal vectors that in fact Andreas mentioned half an hour ago. And I'm not showing the reduction, but in this case, this something happening constructs a huge instance of problem OV, calls it as an oracle, and then returns R, and R is actually whether the given instance is SAT or unsat. So that's how it works. So imagine for a minute that there is a reduction from satisfiability to Duke to reachability, to CFL reachability. It's the same. So if such a reduction exists, it looks like this, right? So X is an instance of SAT, something's going on, and there are calls to CFL reachability for some inputs. So now what I will do is so suppose someone gives me an instance of SAT. I take the protocol for the running of this program, of this code, and I will substitute, instead of these calls, right, to the oracle, or instead of these two library calls, I will substitute certificates. So if U was returning yes, then I will substitute a positive certificate, and if U was returning no, I will substitute a negative certificate. These certificates are subcubic. Therefore, for every instance of SAT, I'll be able to find a certificate. I'll be able to find a huge protocol that actually shows that a given instance is SAT or unsat in time smaller than 2 to the n, significantly smaller. This is basically, so if you have certificates for CFL reachability, this gives you certificates for unsat. And no one knows how to do this. No one knows how to prove tautologies better than 2 to the n in the worst case. So that's how we get our result on fine-grained complexity. That's the intuition. So returning to the summary, and this is the last slide. So let me say that we try to understand why this cubic bottleneck exists for CFL reachability, and we try to find a better algorithm or a reduction that would rule out this algorithm. We don't come up with an algorithm, but we come with the way to solve CFL reachability in some weaker model, we kind of show certificates for yes and certificates for no. And the upshot is that reductions from SAT, which is would be the most natural way to show that, to justify this cubic bottleneck, we show that such reductions are very unlikely. So that's the main summary, and in a sense, I'd say that this is a positive outlook because it kind of gives us more belief that maybe CFL reachability can be solved in subcubic time, in truly subcubic time. Thank you very much.
Okay, thank you for the nice talk. So maybe we have 3 minutes for some quick questions. Any questions from the audience? I have a quick question. In order to understand the subcubic, like the hardness of a CFL reachability, would it be possible to maybe reduce, show a reduction from Boolean matrix multiplication to CFL reachability? And because Boolean matrix multiplication does not admit subcubic, truly subcubic time, combinatorial algorithm. So does that mean that necessarily mean that CFL reachability algorithm does not admit truly subcubic time combinatorial algorithm as well?
That's a great question. I think the answer is yes. And indeed, it's known how to reduce Boolean matrix multiplication to CFL reachability. So most certainly in the all pairs scenario, where here I've been talking about yes, no, but you can do all pairs, and then the reduction is very, very, very visual. And this indeed rules out so-called combinatorial algorithms for CFL reachability that are strongly subcubic. That's true. You can even do this, I think, for yes, no, although you need to somehow do more work. But I think the subtle point here is that the notion of a combinatorial algorithm is somewhat imprecise in the sense that I think people say, well, it's a combinatorial algorithm if it avoids fast matrix multiplication, roughly. And that's why and I think that these results that kind of rule out these combinatorial algorithms, they are important, but at the same time, from the theoretical perspective, we still don't know if there is an algorithm in the sense of, Turing machine, that, any code on, in language written in C, let's say, that would solve the problem in worst case time n power 2.8. So this is something that we don't know. So I think both settings kind of make sense, both the combinatorial and the, maybe more general. And here we are looking at this very strict scenario where we say, well, matrix multiplication is fine, but, can you do anything?
Okay, thank you. That makes sense. Thank you very much. So that will conclude this session. And thank you again for the nice presentation. I will see you in a minute. Thank you.
Thank you.